In today's separations class, we're going to talk about the final topic that we'll talk about in the class. So that's pretty exciting, but also pretty exciting because it's one of my favorite topics, and that is of azeotropes. I've mentioned this a couple of times as we've gone through this semester, but haven't really talked about how to deal with it yet. And in order to address azeotropes, we have to go back to distillation or back to thermally driven separations. Just as a reminder, every mixture that we've dealt with so far has been zeotropic. So in a zeotrope, this is what we might define as normal. We've got a TXY diagram that looks usual. So the pure component boiling points are on opposite ends, and any temperature in between these pure component boiling points, we draw a horizontal tie line and we get phase separation. We get a vapor mole fraction, so YA is there and XA is there. Remember the concept of the bubble and the dew lines. Now this is a great time to go back and review this if you've forgotten any of it or you need a refresher. We can also convert that TXY diagram to an XY diagram to make it easy for distillation problems. So in distillation problems, we could plot the RSOL and the SSOL. And then we could use those lines to stage step our number of stages that we'd need for a certain distillation column. And today we're going to talk about azeotropes. So what happens when the equilibrium data is not so nicely represented? So although this topic of where the equilibrium data comes from is more a topic for phase, I think we can do a little bit of reintroduction. Remember, it comes from Raoult's laws. And because I have two components, I can write two Raoult's laws. Remember, Raoult's law is the YA, which is the vapor phase mole fraction of the more volatile component, times P, the total pressure, is equal to gamma is the liquid phase activity coefficient, times the mole fraction of the more volatile component in the liquid phase, times the vapor pressure of the more volatile component. And I could do the same thing for component B, and if it's a binary mixture, I'll represent YB as 1 minus YA to finish out what Raoult's law looks like. Oops, I said I was going to say XB is 1 minus XA, PB star of T. And for an ideal case, or for a zeotrope, so zeotrope is synonymous with ideal. Well, it doesn't necessarily have to be. I'm not going to say that. I'm going to say all ideal. I'm going to say ideal is zeotropes, but not all zeotropes are ideal, if that makes any sense. So if I have ideal, then my gammas are equal to 1. And when you have an activity coefficient model that does not give you 1, that's where you can possibly have some azeotropes coming in. So for this, I want to go back to all the way back to homework 1 and remind you that we've done something like this already. Remember, in homework 1, I asked you to plot the TXY diagram for activity coefficients that are described by the Margulies model. And there, we found a very weird looking TXY diagram. I think I might have said back then that this was an azeotrope, but again, we didn't really talk about it. The azeotrope is there. So this is what we say when we're talking about an azeotrope. An azeotrope is a certain composition that when you boil it, your vapor phase mole fraction, your YA, is equal to your liquid phase mole fraction, XA. And that can be a problem for separation. So say that you, for sake of argument, let's say I've got a 45% mixture of, what is this, ethanol and benzene, and that's a liquid at 60 degrees or so. And say I boil that, even if I boil it directly to the boiling point, there is no phase separation. I can't draw a tie line there. So that's why azeotropes form a big problem for separation processes. In order to separate them, we have to do some more sophisticated methods. We could still do distillation, but we have to be a little bit more clever about how we do it. So typically in this class, I talk about two main ways that we can deal with azeotropes. We'll talk about one for sure. I'm not quite certain that we'll get to the second one. The first one is called pressure swing distillation, and this will be the topic for next time. pressure swing distillation. Just to introduce the concept to you, distillation, that is going to require two columns operating at different pressures. And a second one is called extractive distillation. And an extractive distillation, that's kind of like liquid-liquid extraction meets distillation. So in extractive distillation, you add a third component. And then you treat it like a multi-component system. So adding the third component breaks the azeotrope, which is good. And then you treat it as a separation of three things. And for that, you need two columns as well. And then another way to deal with azeotropes, I'm going to be very, very broad and vague here and say something else entirely. In other words, don't lose sight of the fact that we have not gone through all of the topics of distillation, all the topics of separation. You're not even close. And hopefully you're seeing the breadth of this field of study as you do your research for your class project. But say I've got a mixture, so like air is a good example. Right, and air doesn't form an azeotrope, but it can be very expensive to distill. There are several alternatives to distillation that you could use to separate air depending on what your specifications are. So you could use a membrane, you could do some kind of absorption process. Those will all work as well. So I want to keep this video a little bit short. I think the best way to learn about azeotropes is to jump into some practice problems, and I've got some of those for you on the sheet today.